Hello and welcome to my talk, where today I'll be telling you about Muppets and more importantly, why you should care. Let's dive straight into my message. So I'll begin with the observation that NLP and database researchers haven't had much to say to each other, at least historically. But as they say, changes are coming. And if I were to summarize what that change is in one word, that would be BERT. Okay, so what's BERT? Well, BERT is a natural language processing model using neural networks that Google developed in around 2018. And it's been applied to search with great fanfare. But beyond Google, the model has been very, very influential across the entire NLP community and beyond. So for example, Bing also uses BERT-like models and calls it a recent breakthrough in natural language understanding. So back to this point. Historically, NLP and database researchers haven't had much to say to each other. Right? So on the one hand, we have NLP researchers dealing with unstructured text. And on the other side, we have database researchers working on structured relations. And it's kind of like, tigers on the one hand and sharks on the other. They kind of do their own thing in their own domain and generally leave each other alone. Right? But of course, Gartner tells us that about 80% of an organization's total data is unstructured data. All right? So in truth, the picture looks closer to something like this, where the tiger has actually a much larger domain. So NLP and database researchers haven't had much to say to each other, but there has been one productive thread of dialogue. Okay, so NLP researchers come and say, hey, look, we can extract entities and relations and facts from free text. And that's a knowledge graph. That's something that NLP and database researchers both can work with and agree on, right? The database researchers say, hey, cool, that's something we can work with. And the NLP researchers say, hey, yes, that's something we know how to build, right? And so in some sense, knowledge graphs serve as a bridge between the two communities. But of course, this is changing. So we see BERT ruling in the NLP domain dealing with unstructured text. You see lots of BERT applications with respect to knowledge graphs. So the question I ask and I want to explore in this talk is, well, what if in the end, BERT took over everything? What would that world look like? Okay, that's the message. And then I'll tell you a little bit about the messenger. That's me. Okay, so I work on lots of things, but if you were to force me to describe what I do, put myself in one bucket, I would say I'm a question answering person. All right. And in fact, I've been working on the question answering problem for over 2 decades, starting in around 1997. So I went to school at MIT, got all my degrees there. This is a picture of my former office, 545 Technology Square, which is where the MIT AI lab was located. Right? So here's an overhead view, and it's that building in red. Interesting note, this is actually the headquarters today of Moderna, the vaccine maker. So my advisor, Boris Katz, had the distinction of building the first QA system on the web. And I was able to dig up some old screenshots. So it behaves as you would expect a QA system to behave. You type in who wrote the music for Next Stop Wonderland, and it gave you the answer. You asked it, for example, who directed Gone with the Wind, and it gave you the answer. Right. So from the beginning, I was absolutely enchanted by this magical technique, magic black box, over 2 decades ago. And you know that scene in Harry Potter where Hagrid comes and tells Harry, "You're a wizard, Harry." It's sort of like that moment for me, except, you know, in this version, Hagrid is saying, "You're going to be spending your career working on this, Jimmy." And basically I have. So I would characterize my career-long quest as trying to solve this problem of connecting users with relevant information. Okay, let me tell you a little bit more. Right? What does that mean? Right? What type of information are we talking about? Okay. My research focuses primarily on text, but throughout the years, I've worked with speech data, images, graphs, semi-structured data, relational data, log data. Right? Now, who are you connecting relevant information to? Right? So in this talk, I'll be primarily focused on general information seekers, but in my research, I've worked with domain experts, legal scholars, historians, data scientists, and a whole host of other stakeholders. So I use the term information access to describe this broad suite of technologies: question answering, search, document retrieval, summarization, that's designed to connect users with relevant information. Okay, so I'm a question answering person, but I also dabble in data management. And this primarily dates back to a stint I had working at Twitter over a decade ago, where I worked on a couple things. One of the things I worked on was analytics infrastructure to support data science. So this is Hadoop-based infrastructure. And I worked on a bunch of data products to connect users with relevant information. So things like real-time search, query suggestion, recommendation, things along those lines. Okay, for the remainder of the talk, I'll be dividing it into 2 parts. First, what is BERT? And second, why should you care? Okay, let's move into the first part. Huh? I can't. I'm recording a talk right now. Ugh. Hang on, I'll be right back. Okay, what's BERT? Well, technically, BERT is a transformer encoder pre-trained with a mass language model objective that generates contextualized representations and can be fine-tuned for a wide range of NLP tasks. I actually don't think that's particularly helpful. That's kind of like asking the question, what's a monad? And getting back the answer, well, obviously, a monad is a monoid in the category of endofunctors. What's the problem? Well, the problem, it's probably too dense to be understood, right? Just like this definition of a transformer for non-NLP folks. So what I'm going to do is I'm going to try to unpackage this for you. And I'm going to do so in 4 steps. I'm going to answer these 4 questions in sequence. The first is, what's a transformer? The second is, what are contextualized representations? The third is, what's pre-training? And finally, we'll get to the notion of fine-tuning. Okay, so let's start. All right, what's a transformer? Well, this is a transformer. Well, this is Optimus Prime. All right. In truth, transformer is a neural architecture that was invented by Vaswani et al. And presented in Europe's 2017. So this is the model architecture for a transformer, but I don't think this is particularly helpful either. So I'm going to boil it down into something even simpler. Okay, so at the core, a transformer is a sequence-to-sequence model, right? So imagine this black box that takes in input sequences and generates output sequences. Now, in NLP, this can be used for a variety of tasks. So for example, machine translation. In comes French, out comes English. Another example might be document summarization. In comes a long document and out comes a short summary. So you can think of this transformer as having this functional form. right? It's a black box that tries to learn correspondences between X input sequences and Y output sequences. If you look inside the black box, this is actually what you'll find. You'll find a bunch of transformer layers organized into two stacks. On the one side, you have what are known as encoder layers. So this is the part of the transformer architecture that takes in the input sequence and generates some form of internal representation. This internal representation then goes to the decoder stack, and from there, the output sequence is generated. Right? And so these transformer layers are where the transformer gets its name. Now, if you focus only on the encoder half of the transformer architecture, you get BERT. Right? So that answers the first question. What's a transformer encoder? Okay. Well, let's move on to the second question. What are contextualized representations? Also explain that by first explaining static representations. Something like word to vect. You've probably seen this before. This has been around for nearly a decade. Okay, so the idea is that you take tokens from natural language and convert them into dense vectors, also called embeddings, that try to capture the meaning of the words in some semantic space. All right. And so once you do this, you can do cute tricks with words. You can take the representation for king, subtract the vector representation for man, add the representation for woman, and get out the vector representation that roughly corresponds to the word queen. Pretty cool, huh? Well, the problem here is that these embeddings are not contextualized. Well, what do I mean by that? Well, consider these two sentences. The crane can lift very heavy loads, and the crane flew quickly across the marsh. Now, you'll notice that both sentences share the word crane, but crane obviously means very different things, right? In the first sentence, it means a construction equipment, a piece of construction equipment. The second refers to a bird. So if you take these sequences of tokens and look up the static representations, the word crane will have the same exact thing. It's probably not what we want, right? So the idea behind contextualized representations is to learn a magic black box where you could feed a static embedding and get out a contextualized embedding in which the vector is adjusted to account for the meaning of that token in the context that it appears in. Okay. Now, where is this magic coming from? Well, if you look inside the black box, you won't be surprised to see that the transformer is comprised of a number of transformer layers. Okay. And the transformer layers works on this, this notion called attention. It's sort of the secret sauce. Now, here's what attention means. Attention means that when I'm computing the representation for myself at some layer in the network, what I actually want to do is to attend to or pay attention to my context, the words to my left, the words to my right. So operationally, this means I got to figure out what part of their representations I got to incorporate to compute my own representations. All right. Now, in a transformer network, this proceeds layer by layer. So you get this, and you compute the next representation, also using attention mechanism, and so on and so forth until you arrive at the end contextualized representation. Okay, so that answers the second question, the notion of contextualized representations. Let's talk about how we start training these models. I'll first talk about pre-training. Now, to explain this, let's go back to the work of Vaswani et al. In the NeurIPS 2017 paper. Right. So they adopt what I would characterize as the just do it philosophy of training. Right. So you start with an initial random initialization of the parameters, and then you just simply train the model with label data. So I would characterize this as supervised training. Now, the problem with supervised training is you can never have enough label data. It would be awesome if we could move into the realm of unsupervised training. That's like the holy grail, right? Well, as it turns out, self-supervised training can be just as good. And in the context of natural language, there's a very simple thing you can do. You can predict the next word. Now, a fancy way of saying this is a language modeling objective, but that's what it is. Guess the next word. Right? And the beauty of this is that if you self-train in this way, you don't need labels. You just need a lot of text. Right? The label for a sequence is the next word that comes in that sequence, and you just look ahead. Okay, but an objection you might have is, well, I don't really care about the task, right? Guessing the next word, yes, type ahead, I probably need it, but it's not generally useful, right? But as it turns out, it really doesn't matter, and I'll come back to that point in a bit. Okay, so instead of predicting the next word, BERT introduced an innovation that's even smarter. It's called mass language model. And it's actually a really easy idea. So here's what you do. You take an input sentence, all right, and you cover up a word. More formally, you mask it. And then you ask the model to guess what that word is. Okay, so in essence, this is what you're doing. You're starting with a lot of text, this, and you're playing the peekaboo game with the model, like the same game that you play with infants and toddlers. So you play peekaboo with respect to covering up words. You do this many, many, many times, and with lots of GPUs. And at the end, you get the magic of a pre-trained model. Okay, so the TLDR is this. Vaswani et al. Started off with random initialization of the parameters and directly engaged in supervised training. With BERT, it has the benefit of mass language model pre-training. And so at the end of the pre-training phase, the model already knows a fair bit about general properties of language. Okay, so that explains point number 3, pre-training. So let's move on to point number 4, fine-tuning. All right, so here's where we are currently. We've done pre-training. We played the peekaboo game with the model. So this is self-supervised. But how do we get BERT to do something more interesting, right, other than predict the next word? Well, this is where fine-tuning comes in, right? So with fine-tuning, what you're doing is you're adjusting model parameters based on label data from a downstream target task, right? So this now brings us to the realm of supervised training. Okay. BERT is used primarily in 4 different ways, and I'll describe them to you in these next few slides. So one simple way of using BERT is single input classification, right? Something like a sentiment analysis. It would have the functional form that looks something like this. Okay, so that's take the BERT model, and that's feed it a sentence like, I really like this movie. And our goal is to get out a class label. In this case, something like, oh, this expresses positive sentiment. Right? Way number 2 of using BERT, single input sequence labeling. So this is something like named entity recognition and has the following form. Right? So let's take the model. Let's stuff into it a sentence like, we hire Mary to do the job. And the output, what we want to do is to label each token. And these labels tell us where the named entity is, in this case, a person. Okay, method number 3. You can use BERT for 2 input classification tasks, like paraphrase detection. Okay? So you can start with having this functional form. So you can start with the BERT model, you can throw into it two different sentences like I love cats and I love dogs, and the model will do classification and tell you these two input sequences have different meanings. Okay. And then finally, method 4 is you can use BERT for two input sequence labeling, something like a question answering. And it has this functional form. So once again, consider the model. What you're doing here is you're feeding into it a question and a candidate piece of text that may have the answer. So something like, when was Albert Einstein born? And then a passage like Albert Einstein was born in 1879. And the output is that the model will label the location of the answer for you, in this case, 1879. Okay, and that's fine tuning. So after pre-training, you do fine tuning, and that's where you get BERT to actually do something useful. So I've covered all 4 points, and now you know what BERT is. Okay. But BERT isn't just one model. The really interesting thing about BERT is that it spawned lots of innovation. So after BERT came lots of different models that are sort of BERT-like, and I'll tell you something about them. Right? So first is, what's a Muppet? Well, BERT is a Muppet on Sesame Street. And so as a result, NLP researchers have named their models after other Muppets on Sesame Street. So there's Ernie, there's Big Bird, and there's a whole bunch of other models with similar names. And so a Muppet-based model is just a cute phrase I like to use to refer to BERT-like models. Okay, GPT-3. Well, so this is a model that's grabbing a lot of headlines recently. So here are just some of the things that the people on the web are saying about it. It's revolutionizing artificial intelligence. Is it closing in on human intelligence? Are we getting to general AI? Okay, so I'll try to demystify that for you. Okay, so let's consider the transformer architecture with a stack of encoders and a stack of decoders, right? So if BERT is the encoder part of the transformer architecture, then GPT, the family of models, represents the decoder half. That's the basic architecture. Right? So GPT, the family of models, is essentially a pre-trained decoder portion of a full transformer architecture. Now, the special thing about GPT-3 is that they've taken the route of throwing more data and building bigger models at the problem. So here's a growth in model parameters over the years, and GPT-3 has 175 billion parameters, something that even would make Dr. Evil proud. Right? So there was a blog post from NVIDIA that just came out recently. It said, well, when GPT-3 first came out, it would have taken 7 months to train with 512 V100 GPUs. But today, it'll only take you a month using 1,024 A100 GPUs. Yay, look at the improvement. Okay, so if BERT is the encoder part and GPT is the decoder part, well, what happens if you have both parts? Well, that's basically T5. So T5 is the full encoder-decoder architecture that's been properly pre-trained. The interesting thing about T5 is that it phrases everything, all natural language processing tasks, as sequence-to-sequence transformations. Right? So if you want to translate a sentence from English to German, you put it in this input template and you tell T5 to do it. If you want to determine if two sentences have the same meaning, you would put it in the template and then ask T5 to tell you the answer. And same with summarization. Right? So that's the contribution of T5 and how it works. Okay, so as a recap, here's a rough timeline of how these developments progressed. So vanilla transformer, the Zwanny et al., was introduced in 2017, and they had no pre-training. GPT-2 was actually the next model that came around. It was introduced in mid-2018. So it's the decoder portion of the architecture, and it was pre-trained with the predict next word task. Late in 2018, we saw BERT, which, as I explained, is the encoder portion of the transformer architecture, and it's pre-trained with the peekaboo game. All right. In late 2019, we saw the introduction of T5, which is the fully pre-trained encoder and decoder parts. And mid-2020, we saw the introduction of GPT-3, which is like GPT-2, but bigger. Okay, so now you know all about BERT and his Muppet friends. Hang on, what? Okay, so sorry about that. No more interruptions, I promise. Okay, let's see, where was I? Okay, so I've told you about BERT and his friends, and now comes the most important part. I'm gonna try to convince you why you should care. Okay, so I'm gonna do so by presenting a number of case studies of the capabilities of BERT. So I'll start with this one. So BERT is good at text ranking. What do I mean by that? You give BERT a whole big pile of documents and you send it a query like, what is a lobster roll? And you get back a pretty good answer. A lobster roll is a bread filled with bite-sized chunks of lobster meat, yada, yada, yada. So how do you do this? Well, you start with a pile of text, and then you select some promising text out of that big pile. And then you run it through a second stage to re-rank the selected text, and then you get the text that you're looking for, the relevant text. Now, for the first stage is pretty simple. You can just do something like Lucene or Elasticsearch, something just based on keyword retrieval. And as you would expect, the second stage is based on BERT. Okay, so how does this work? Well, actually, I've showed it to you already a few minutes ago. So we can use BERT as a relevance classifier. So it's using this functional form here that I presented before. What we do is we take a query and a bunch of candidate texts, and then we feed it to the model, and the model tells us the probability of relevance, right? So we do this for a query and a bunch of candidate pairs, and then we sort the results based on the probability of relevance. Okay, so I made a claim, right? BERT is good at text ranking, so I should back that up and say, hey, like how good? So I'll present just one case study, ranking on the MS Marco passage dataset, which comprises 8.8 million passages with queries drawn from Bing logs. Okay, so MR is a metric. Don't worry about it. It's not important what it really is. Just think higher the number, the better. Okay, so if we just do keyword search like BM25, we get a score of 0.165. Right? Before BERT, the best model at this task was called IRNet. It's a deep CNN and IR hybrid, and it gets 0.281 on the standard benchmark data set. With BERT, this number, this effectiveness jumped from 0.281 to 0.359 using a the mono BERT model proposed by Nogueira and Cho in 2019. Okay, now I want to emphasize here that this gain, this jump of about 30%, came from one single innovation, right? That's BERT. And so literally scores went up by 30% overnight. That's how good this technique is. Right? And fast forward the current state of the art, where for this data set, we're at around 0.426. And so that's another 20% gain. Okay, the second claim, BERT is good at question answering. Okay. So what do we do in question answering? Well, we start with a pile of text. We ask a specific question like who lives in the Imperial Palace in Tokyo? And the output is not only a passage of text, but the exact answer here highlighted. The Imperial family is the answer. Okay. How do we do this? Well, we can do this using basically the same two-step process. Right, start a pile of documents, select some promising text with Lucene, and then you use another module to extract the correct answer span. And as you would guess, this is also based on BERT. Right? How does this work? Actually, I went over it a few minutes ago. All right, so it's using this functional form of BERT. What we do is we take a question and a candidate answer, and we feed it to the model, and it generates a bunch of probabilities of this particular token position being the start of the answer and the end of the answer. And from that, we can infer the exact span of the answer. Okay, I made a claim. BERT is good at QA. So let me justify that. Like, how good? So this is a standard benchmark data set called Squad. And here we're answering questions against about 5 million Wikipedia articles. The metric that we care about here is something called exact match score. Think about it in terms of accuracy. Once again, it really doesn't matter what the metric is. Just think higher the number, the better. Okay, so pre-BERT in a system called Dr. QA, the effectiveness was around 0.271. With BERT in a system called BERT it jumped from 271 to 0.386. And once again, this is one single innovation directly attributed to BERT. And the state of the art is around 0.57 currently. So we've advanced quite a bit over the last couple of years, still primarily based on models like BERT. Okay, so let's take a step back a bit and ask ourselves the question, what is QA? Okay, so I'm gonna ask you to sort of contort yourself a little bit, squint a little bit, and use your imagination. Okay, now it seems to me that QA is kind of like select project queries. Yeah, right? So who lives in the Imperial Palace in Tokyo? That's kind of like this. That's interesting. Okay, let's go on. BERT can also do what is known as multi-hop QA. What's that? Well, like a QA setup, you start off with a pile of documents. You ask a question like this: which former member of the Pittsburgh Pirates was nicknamed the Cobra? So you go through documents and you find this particular paragraph, and it says several current and former players are John Milner, Dave Parker, and Rod Scurry. That offers some information, but it doesn't give us the actual answer, right? Because we need to piece it together with another paragraph, right? So the first paragraph gives you the roster, and the second paragraph actually tells you the nickname. Right, so this is why it's called multi-hop, because you need to assemble information from multiple paragraphs. Okay, let's go through the same exercise. What's multi-hop QA? So once again, if you contort yourself and use your imagination, that seems to me a little like select project join queries, right? It's kind of like this. Oh, that's an interesting observation. Okay, let's move on. Right, so we've established BERT is good at QA. Okay, now this is something what NLP folks call the open book question answering condition. It's open book in the sense that you have a corpus that you're looking for the answer in. Right, so you can use Lucene keyword search to grab a whole bunch of paragraphs and then examine them in detail using BERT. But however, there's another condition known as closed book QA, in which you just have the model. The model is not allowed to consult a corpus or any text at all. And as it turns out, one of these BERT variants, T5, is actually really good at closed book QA. Okay, so let's think about that for a minute. There's not anymore a corpus, just the model. Okay, so closed book QA with T5 looks something like this. You have a black box. In the input goes a question, and the output, an answer comes out. All right, and if you look into the black box, it's just a transformer. So no more corpus, just a transformer. So this is sort of like the scene in the Matrix where the little boy tells Neo that there is no spoon, right? There is no spoon. There is no corpus, just a transformer. All right. So with T5, you can do QA in this closed book setting. However, you still need pre-training and you still need fine-tuning. Okay, so the next step, can we get rid of that? Right, so there is no spoon. No, that's changed it to there is no fine-tuning, just a pre-trained transformer. Well, how do we get there? Well, let's step back a bit and go back to BERT and ask the question, what exactly does BERT know? Well, BERT is pre-trained using this peekaboo game, right? So it stands to reason that you can convert it into a way of probing BERT to find out what it knows. Okay, so let's take a relation like P19, which is the place of birth from Wikidata. Okay, so here's what we're going to do. We're going to phrase a question in the form of a statement with an empty mass token. Okay, and since BERT is really good at the peekaboo game, we're going to send it to BERT and just ask BERT to fill in the blank. All right, and so if you do this, you get an accuracy of around 16%, which kind of sucks, right? Because if you were to issue like an SQL query like this, you better have an accuracy of 100%. Okay, so in this respect, BERT isn't doing very well, right? But this is pre-training only. Right? Well, what if we could feed BERT facts directly? Let's teach it facts directly. And as it turns out, under the right circumstances, BERT can actually memorize relations, memorize facts that you feed it. So with the right architecture, BERT can memorize a couple million statements with accuracies above 90%. Okay, let's do the same thing. Take a step back and think a bit, what's fact memorization? So if you contort yourself, lose your imagination a bit, to me, that kind of looks like inserts, like database inserts. Okay, so let's take stock of what we have already. Right, so QA is select project queries, multi-hop QA, you can add joins to the mix, fact memorization with BERT, those correspond to inserts. And what's cool, we can do it without the corpus. We've gotten rid of the data. Okay, so what are the implications of these kind of interesting observations? Let's take a step back a bit and ask ourselves, what exactly is an RDBMS? Well, an RDBMS at a really high level is just a sequence-to-sequence model, right? It's a black box that has an input and an output. In comes SQL queries, right? And out comes the answer. Now let's compare. What's a QA system? Well, a QA system is also a sequence-to-sequence model, right? It's a black box where you have inputs and outputs. In comes natural language questions, and out comes the answer. Interesting. Okay, well, so how would you do this, right? So one simple way of implementing a QA system is to have an internal query rewriter that takes the natural language question and converts it into a SQL query, and then issue the SQL query against the database, and then out comes your answer, right? And in fact, that's already being done. In the NLP community, there's a benchmark called a spider benchmark, and it's all about semantic parsing and converting natural language text to SQL queries. All right. So here's one of the queries that's contained in the data set. And you can see, well, it's pretty sophisticated. And neural network models today do fairly well on these tasks. This is already being done from another perspective also. So here's the answer to the question of what does 175 billion parameters get you? So if you recall, that's GPT-3. And there's evidence that GPT-3 can write code based on natural language descriptions. Here's somebody that played with it and is showing an example on Twitter. You can look up the tweet yourself. So you can say something like, I want to describe a particular layout. I want a button for every color of the rainbow, and GPT-3 writes the code that does that for you. That's pretty cool. Okay, so back to this picture I presented in the beginning, right? So on the one side we have NLP, on the other side we have databases. So can we imagine a magical black box, right? That's able to ingest unstructured data and structured data and allow the user to type in questions that look like this and get out results that look like this, right? In other words, natural language access to all of your organization's data. Hey, and you know, what if we build it out of transformers? All right, so this question I posed in the beginning, what if BERT took over everything? All right. The more accurate form of that question is, what if transformers took over everything? Now you might be thinking, this is absolutely nuts. But I don't think this is such a far-fetched idea. Right? In fact, there's a paper coming out in VLDB in which the authors propose something called NeuroDB, which discusses a lot of the same ideas that I'm talking about here. All right, so let's talk about RDBMSs based on neural networks. Is it really that far-fetched? I think the answer is no, because I don't think this is fundamentally very different from model-based approximate query processing. And techniques like this have been around for more than a decade. All right, so this is what I'm proposing. All right, a magic black box that is able to ingest all your organization's data and provide natural language access, all based on transformers. Okay. And you know what? As I've just demonstrated, a lot of the pieces already exist, right? So in some sense, we're already building this. We've begun to build this. Now, you got to remember, when these things were first being built, they were a far inferior form of transportation than what came before. But over a century later, look how far we've come. Okay, so in conclusion, here's what I'm proposing. Transformer DB, because this is just what the world needs, yet another database, right? So Transformer DB is a neural network that ingests all your organization's data and allows you to query it using natural language at transformerdb.ai. And by the way, we're looking for a seed round.